Hello students, welcome to another video of matrix space. Today we will discuss the closure of set. Next definition is closure of set. Closure of set. So first of all we will take the definition of closure. Definition of is closure of set. Let XD be a matrix space. Let XD be a metric space and A is subset of X, then closure of A is denoted by a closure and it is defined as the union of A and the set of all limit points of A and the set of all limit points of A. So a subset of matrix space XT is said to be closure of that set A whenever that set is equals to A union of A together with the set of limit points. So A union limit points of A, that is we can write A closure is the set of A union limit point of A, or in other words we can say that A closure is the set of all points of A together with all those points of A with all those points which are arbitrarily close to A. A closure is the set of all limit points of A together with all those points which are arbitrarily close to A. This is the definition of closure of set A. A closure is denoted by A bar and is the union of A with limit points of A, or in other words we can say that A closure is the set of all points of A and the points which are very close to A. This is the definition of closure of set. Now we will take one note. In short, if we see the definition clearly, then A union limit points of A, and by definition of limit points we know that the interior point as well as boundary point is the set of limit point of set A, and in the most of the cases A limit point of A contains all of the elements of A. So A closure, in most of the cases A closure is equals to set of all limit points. So first note is A closure is closed set. A closure is closed set. First note is A closure is itself closed set. Now this is, I am taking this A closure is closed set is theorem. You can prove that this A closure is closed set. Now we will take one example that for your homework, find the closure of first set of natural numbers. We have to find the closure of set of natural numbers. Second, the closure of integers. Third, you have to find the closure of suppose rational numbers. So these three are for your homework. One hint for this homework is A closure is the set of A union limit points of A. In most of the cases, A closure is equals to set of all limit points of that A. So, this is for your homework. Now, we will see the theorem and also one example for your homework. Find the closure of any finite subset of metric space. Find the closure of any finite subset of metric space. Find the closure of any finite subset of matrix. If you have given a finite subset of metric space XD, find the closure of that set. These two examples for your homework. This is suppose first one, this is second. Now, we will see the theorem. Statement of the theorem is, let XD be a metric space. Let XD be a metric space and A is subset of or A is contained in metric space X. Then A is closed. XD be a metric space, A is subset of whole metric space X. Then A is closed. We say that a subset of metric space is closed if and only if A is closed set, if and only if A is equals to A closure, if and only if A is equals to A closure. Now, to prove this result, we have given that XD is metric space, A is subset of X, and we have to prove A is closed if and only if A is equals to A closure. This is if and only if type theorem. So, first of all, we will consider A is closed set and we will prove A is equals to A closure and conversely. Now, suppose first of all assume that A is closed, A is closed set. Now, A is closed set and we have to show that our claim is, here our claim is A is equals to A closure, A is equals to A closure. Now, our claim is A is equals to A closure means we have to show that A is subset of A closure and A closure is subset of A. Then we can say that A is equals to A closure. A is contained in A closure and A closure is contained in A, so A is equals to A closure. Now, here we have given that A is closed set. Since this A is closed set, A is closed set. So, A is closed implies A contains all its limit points by the theorem of limits points. We know that A is closed, then A contains all its limit point. So, A is closed implies A contains all its limit points. A contains all its limit points. But this A closure, by definition of A closure is the set of all limit points of A union A. So, A closure is the set of all limit points of A. A closure is the set of all limit points of A. This implies A contains all its limit points and A closure is nothing but the set of all limit points. So, A contains this A closure. So, A closure is contained in A, but A is contained in A closure always, because A closure is the set of union of A with limit point of A and A is always in the limit point. So, A is contained in A closure always. So, A closure is subset of A is subset of A closure implies A is equals to A closure. Hence, the first part is proved. In the first part, we have to prove, we have suppose A is closed set and we have to prove A is equals to A closure. To prove A is equals to B, we just prove that A is subset of B and B is subset of A. So, here we have to show A is equals to A closure. Now, here A is closed set and by theorem on the limit points we know that A is closed, then A contains all its limit points. So, here A is closed, so A contains all its limit point. A contains all its limit points means set of limit point is contained in A. So, here A closure is the set of all limit points and A closure, A contains all its limit points. So, A closure is contained in A, but A is contained in A closure always. Therefore, we can write A is equals to A closure. Now, conversely, we will suppose A is equals to A closure and we will prove A is closed. Conversely, suppose that A is equals to A closure. A is equals to A closure. This implies that this A is equals to A closure and A closure contains all its limit point. A is equals to A closure and A closure contains all its limit points means A contains all its limit point. Suppose A is equals to A closure, but we know that A closure contains all its limit points. So, from this we can write A contains all its limit points because A is equals to A closure. A contains all its limit points, and we know that A is closed if and only if it contains all its limit points. So, A contains all its limit points means A is closed set. A is closed set. Hence, the converse part is proved. Now, in this converse part, we just suppose A is equals to A closure. We know that A closure is this set of A union limit point of A. So, A closure contains all its limit point, but A is equals to A closure. A is equals to A closure means A contains all its limit point, and we say that the set A is closed if and only if it contains all its limit points. So, A contains all its limit point implies A is closed. So, converse part is proved. Now, the next theorem is A closure is the smallest closed set. A closure is the smallest closed set containing A. Containing A. There is similar theorem that we have discussed in interior of set. A interior is the largest open set contained in A, and now here we are saying the statement A closure is the smallest closed set containing A. So, this A closure contains A, and in that theorem we have seen that A interior is the largest open set contained in A. So, there is a difference in between these two words, contained and containing. So, we have to prove that this A closure is smallest closed set containing A. To prove any set smallest or largest, we just take the another set and prove that first one is containing second. To prove A closure is smallest, if you take any another subset which containing A, any another closed set of that metric space which containing A, then this A closure again contained in that set. Thereafter, we can say that this A closure is smallest closed set. Now, we will prove this theorem. The proof, we will take another closed set of metric space XD containing this A. Suppose let that F be any other closed set containing this A. We have to show that A closure is the smallest. So, if we take any other closed set containing A, then this A closure must be contained in this F. So, here A we have taken F be any closed set containing A means F contains A, that is A is contained in F. Here F be any closed set containing A. So, F contains A. Now, our claim is A closure is smallest, that is our claim is A closure is again contained in F. Now, we have to prove A closure is subset of F. For that, we have to take one element of A closure, and if that element is again F, then we can say that A closure is subset of is contained in F implies A closure is smallest. Now, if we take A belongs to A closure, let X belongs to A closure, and by definition of A closure, A is equals to A union set of limit points of A. A union set of limit points of A. Now, here there are two possibilities, either our X belongs to A or X belongs to limit point of A. So, first case we will take this X belongs to A. Now, X belongs to A implies that write one this implies either X belongs to A or X belongs to limit point of A. So, first case is X belongs to A. Now, X belongs to A and this A is subset of A is contained in F. So, x belongs to A and A is subset of F implies the elements of A are the elements of F implies x belongs to F. We have to prove A closure is subset of F. So, our x must, we have to prove that x is again the element of F. So, if x belongs to A, then that x belongs to F implies our A closure is subset of F. In this, therefore, we can write A closure. After only first step, we can say that A closure is subset of F. We have to prove x belongs to A, then x belongs to F. Also, x belongs to A limit point of A, then x belongs to F. So, from both the cases, we can say that A closure is subset of F. Now, we will take the case second. If x belongs to set of limit points of A, x belongs to limit points of A. Therefore, by definition of limit points, by definition of limit points, for every r greater than 0, SR of x intersection with A must be non-empty. By definition of limit points, SR of x intersection with A is non-empty. So, here by definition of limit points, there exist r greater than 0. By definition of limit points of A, there is for all r greater than 0. Definition of limit is for all r greater than 0, SR of x intersection with A is non-empty. Instead of this, you can write SR of x minus singleton x intersection with A is non-empty. Instead of writing this SR of x intersection, write the proper definition SR of x minus singleton x. So, our SR intersection of this open sphere and A must contains a element other than center. So, SR of x minus singleton x intersection with A is non-empty. So, here the intersection of this open sphere and A contains other points than center. So, again A is subset of F. So, this SR of x minus singleton x intersection with F again non-empty, because A is subset of F. This implies SR of x minus singleton x intersection with F is not equals to phi. Intersection with F is not equals to pi. So, this implies that x is the element of limit points of F. So, x is the element of limit, by definition of limit point, again in this open sphere without center intersect with F is non-empty, implies x is limit point of F, implies x belongs to F. We can write x belongs to F because limit point of F is contained in F. This we can write limit point of F is contained in F because this F is closed set. So, instead of writing this, we can write this x belongs to limit point of A, but x belongs to set of limit point of F, but F is closed. F is closed. So, this implies limit point of F is contained F. F is closed means F contains all its limit points. So, F limit point of A is contained F implies x belongs to this F limit point of F, and limit point of F is subset of F implies x belongs to F. Hence, whenever if our x belongs to A, then again x belongs to F. Similarly, if x belongs to limit point of, that is x belongs to limit point of A, then x belongs to F. From both the cases, we can say that therefore, from both the cases we get A closure is subset of F. Hence, A closure is the smallest subset. A closure is the smallest subset of X metric space XD containing A. This statement and the statement of interior points, the statement was A interior is the largest open set contained in A. Both statement makes confusion in the examination. So, there is a difference in between those statements. So, keep these things in your mind. Now, the next example is show that SR of X open sphere, SR of X closure of open sphere is contained in SR of closed X. Closure of open sphere is contained in closed sphere. This is again for your homework. You have to prove this is subset of this. That is for that you can take one element of this set, and that you have to prove that again that element is in this set. This is for your homework.